Thank you for the introduction, Jingwen. Welcome to my PhD defense. The title of my thesis is Early Detection of Business Rule Violations, and I'd like to extend a warm welcome to my advisor, Jingwen Su, and also my committee professors, Tevfik Boltan and Daniel Lokshanov. The setting of the problem I study is looking at when event streams must satisfy some business rules. So we imagine that a business has a set of workflows that they complete to serve some customer. And when the activities in these workflows are completed, they generate event streams. So for example, there might be a user who makes a request at one time, then later makes a payment, and we say this constitutes an event stream, some ordered events. Also, we might have another user from a different workflow enactment, Bob, who makes a request and then makes a payment at a later time. The event streams from these workflows are subject to some business rules, which might be organizational goals like making money or serving customers well, maybe resource limitations, or safety regulations that are imposed by laws. And the high-level idea is we want to observe these event streams at runtime and determine whether or not they satisfy the rules or violate the rules. So for example, in the event stream on the bottom, maybe the rule states that if payments are too late, this is a rule violation, and Bob's enactment violates a certain business rule for making a late payment. The rule specification language we use is logical. The fundamental characteristic is that it has events, which you can see an example of with the request. So we'll associate an event in the event stream with one of the atoms in our rule language, which can take various attributes from that event. So for example, we match this request to a certain user at a certain timestamp X. A particular feature of the rule language I've been interested in developing is looking at these quantitative time gaps. So identifying if I have two timestamps associated with events and some integer difference between them, along with maybe an equality or an inequality. So in the rule, we'll have both data variables, which would just hold a constant, like a user's name or the ID for their account. And we also have these time variables that we add these time gap inequalities to. The semantics of the rules are given by looking at the rule in two parts, the body and the head, which are separated by the implication arrow. And we would say the rule body on the top has two event atoms for request and approval event with one time gap, and the rule head has
Is that Marines?
I don't know. The rule head has a payment event, a receipt event, and those events satisfy the two gap atoms. And specifically, within the rule, the commas represent conjunction. So the body is a conjunction of these constraints, and the head is a conjunction of these constraints. And they're matched by implication, or they're joined by the implication arrow, which would say, anytime I have a satisfying assignment from the events to the rule body, we need to observe an assignment to the atom, to the variables in the rule head. So for example, for the event stream, if I just have Alice making a request at time 1, this matches the event in the rule body, but we don't have a corresponding event for the approval. We don't have a corresponding approval event, so this event stream vacuously satisfies the rule. Alternatively, for this event stream, we have request approval events where their time gap is greater than 1. And also we have payment and receipt events from some other user which satisfy the time gaps. So we would say this event stream satisfies the rule because for the assignment to rule variables in the body, there's another assignment to the rule variables in the head. Existentially quantified. The free variables in the head are existentially quantified. And we allow the universal variables in the head to appear in the body, to appear in the head. So notice that V in the head appears. So the time gaps, or also the data in the rule body, can constrain the events in the head.
And in the payment, for example, when you say user V, those are not, like, we don't have a type for those, right? Those are just like atoms. It's not like I could put, for example, Alice a request or payment Bob, comma, V, where V is the amount of the payment, and put a constraint on V in terms of that payment versus a later payment. Arithmetic, do you have
we do allow a domain that has some numeric data.
Oh, you allow that?
Yes.
Okay. In addition to time constraints, you can also have constraints in related to that.
Yes.
Okay.
And I cover that towards the end
Okay.
when I talk about.
So that's that. Yeah.
Yeah.
It's a relational tuple. There's no nesting.
There's no.
For the value, I mean the attributes inside payment is just a tuple. It's just a relation.
Yeah, sure.
No information. That's all.
But some elements could be
Could
typed
be,
like
yeah.
integer, whatever, and you can have constraints
That's
about
right.
it. Yeah.
Yes.
That's what.
Yeah. So
In addition to time constraints, which I understand.
Yes, but mostly my techniques focus on the time constraints.
Yeah.
So, given this rule language, our motivation is to detect rule violations at the earliest possible time. And I want to illustrate what earliest means. So for the rule from before, this request and approval leading to some payment and receipt, if I've only observed a request and approval at times 1 and 2 respectively, if I instantiate y with the value 2 from approval, we have an upper bound on when z can occur because of the first atom in the head. The z is less than or equal to y plus 10, gives me z has to be less than or equal to 12. So that means my payment needs to be observed by time 12, and it follows that if z is upper bounded by 12, w is upper bounded by 14. And so I have, just from observing the body assignment, I have some deadlines for the events in the head. And the earliest deadline, the earliest of these deadlines will be the earliest time I can declare that a violation has occurred. So in this case, if I don't see any other events, at time 12, I can say, okay, a violation has occurred, and earlier I can't. Similarly, if we then see a payment event at time 11, a payment event at time 11, z will be instantiated with 11, and then the upper bound on w, the remaining variable, is 13. So if I update the event stream with events for the head, I can get different deadlines. And so now, given this event stream, previously I was waiting for time 12 to declare a violation, observed a event at time 11, and now time 13 is the earliest time I can say there's no possible way to satisfy these constraints. So our definition is an event stream E is a violation of a rule. We also look at a set of rules if there's no extension of the event stream that satisfies the rule or each rule in the set. And when we say extension, we mean later in time. So if I have the current event stream, assuming all the events that can come will have some later timestamps, then is it still possible that I can satisfy all the rules? And it's a violation if there's no possible extension that satisfies the rules. So the question I look at my thesis is, can we detect violations at the earliest possible time? My work is organized mostly by what types of rules I study this problem for, and that organization also gives us the outline for my defense. So first, I'll talk about rules without data, which I covered in my MAE, but from, as Jingwen said, comments from other people that I met, I was pointed to related work that I could then compare my MAE work to, so I'll present that comparison. Then I'll talk about sets of rules with data, where for my proposal, I showed how to do this sort of violation detection for individual rules, but since then we've extended that to sets of rules by using a chase algorithm or a chase process, which I'll cover in the second section. Then I'll talk about adding aggregation functions over numeric data, and specifically where I develop some different types of time windows. So if we aggregate a set of events, it'll be events that are collected in time. And then finally, we'll talk about the early detection problem for unrestricted sets of rules, so the most general problem with that rule specification language, and we show that that is impossible through an undecidability result. So first, the results for rules without data. So Kamp's theorem shows us that we have a translation from dataless rules into LTL, where Kamp's theorem, given in his thesis in 1968, stated for any dataless rule, there is an equivalent LTL formula, which for the purposes of violation detection means we can translate a dataless rule, meaning we only have timestamps, into LTL. Then there's a corresponding translation into a finite state machine. And then the finite state machine can act as a monitor, either by detecting whether or not an accepting state. Yes?
When you say dataless, but events still have names, or like so you can still say, you know, assuming cat at 5 o'clock, there should be dog at 7 o'clock.
Yes.
Yes.
Yeah, so we have the event name and then the time variable.
Is the only
Yeah.
Right.
And we still have the rule head goes to the rule body. We just don't have any other contents. Each event is basically just a unary, each event type is a unary relation over the set of timestamps.
Okay. So there's another thing, is you're citing, you know, Kamp's thesis. Well, it seems from your thesis that these rules are your own definition, right? So how is it possible that there is a theorem from 1968 that is formulated like this? I mean, it has to be some consequence. I mean, you must have done some translation between your rules, between your language and what Kamp's theorem actually says. So can you tell me what Kamp's theorem actually says?
So to address the question, the statement there is adapted to my setting.
Oh. Right, okay.
And Kamp's theorem is it covers a much wider class of formulas. But this is, in my context, it says a dataless rule has some equivalent LTL formula.
Okay. We'll come back to that later.
Okay, and in my thesis, I give the actual statement of Kamp's theorem and show how that produces this, or this follows from the original statement of Kamp's theorem. So Kamp's theorem tells us that this problem is solvable, but it doesn't exactly give a clear way of constructing the actual formula. It just says one should exist. There have been a number of proofs of Kamp's theorem that attempt to make it more clear, because Kamp's original proof was over 100 pages. So further proofs try to simplify it and to give more constructed algorithms. And in 2014, Rabinovich gave a translation derived from Kamp's theorem that said this translation will result in LTL formulas that are hyper-exponential in the size of the input. Just means they're larger than any exponential function.
So also just a question, so 68, so in Kamp's result, there is a linear time logic that is equivalent to our current understanding of, because I mean, I think there are so many variations of LTL, and there's the one basic one I use, for example, in my classes, and I think Punelli was the guy who kind of like made that, so it's equivalent in Kamp's thesis, that
Yes,
equivalent definition.
Kamp's thesis doesn't state it as linear temporal logic with the next and until and future operators that we're familiar with.
Yeah.
But the temporal logic that he does use is equivalent to LTL.
Yeah.
So given this proof, we can say, okay, well, this is work only identified after the MAE, that this translation from Kamp's theorem and then from Rabinovich is hyper-exponential in the size of the input rule. And then we did complexity, yes?
So when you say hyper-exponential, do you mean just faster than 2 to the n, or faster than 2 to the 2 to the 2 to the 2 to the n for any tower?
For any tower.
Okay.
It's the quantified automation.
Okay. Sure.
So for any exponential function. So we did a complexity analysis of the translations in our MAE, and we show that for subclasses of dataless rules, specifically singly linked acyclic dataless rules, there's an equivalent formula whose size is single exponential. And for singly linked rules, there's an equivalent formula whose size is double exponential, where singly linked and acyclic I defined in my MAE in the thesis, and it's a syntactic characterization based on kind of the structure of the time variables within a rule. So that concludes the section 1. Next, I'll talk about extending the work I presented in my proposal to sets of rules, no longer individual rules, using a chase process. So the problem is that if we consider a violation of a set of rules rather than just individual rules, the interactions between the set of rules can lead us to detect violations earlier. And an example would be if I have two rules, A and B, request at time X leads to some payment at time Y, that's later. And then rule B says if there's a request and a payment where the gap between the request and payment is at least 5 timestamps, there's an approval that came before the request. So if I were a request at time 10, then this tells me I need to see a payment event sometime in the future, later than time 10, in order to satisfy rule A. But if time 15 comes, if our clock says, okay, time 15 has passed, that means this payment event now the timestamp for the payment must be greater than 15, because we always assume events can only appear in the future. And then this request event and the payment event will trigger the body of rule B, which tells us we need to see an approval event in the past of time 10, which says there's a violation. So to note here, there's no violation of A at time 15 because I can still see a payment arbitrarily far in the future. And there's no violation of B alone because I've only seen a request event. I haven't seen a payment event with it. But the set of rules A and B is violated. So there's no extension of just this event stream with the request. There's no extension after time 15 that satisfies the set of rules. So we realized this, we said, okay, our individual rule techniques no longer apply. Maybe we can use this creation of what we call expected events to say if I expect an event to occur in the future and I can reason about what time gaps it has to satisfy, this can tell us if a set of rules has some violation. And to create expected events, we use the chase process, which is an algorithm from 1979 or 1980 that was developed to reason about database dependencies, but we're applying it in a novel context in violation detection, and this to event streams. So for the same set of rules, if I have a request at time 10, I can identify that the assignment U to Alice and X to 10 satisfies the rule head, and I chase rule A by instantiating the existential variables in the rule head. So payment has some Y, an existential variable. So I'm going to instantiate that with some marked variable Y prime, which is some specific but unknown value for Y that is greater than or equal to 10 in order to satisfy this request. Then we'll chase the request and payment with rule B and that new marked variable Y prime to get there's some approval at a Z prime where Z prime is less than or equal to 10. And additionally, we remember that this approval was generated with the assumption that 15 was less than or equal to Y prime. So when we chase a rule with an assignment, we carry forward any assumptions that that chase process made. So when I chase B, I have that X plus 5 less than or equal to Y time gap. I'm going to include that in this expected event because this event is only expected under the assumption that 15 is less than or equal to Y prime.
So is Y prime carried forward symbolically, or is it instantiated with like different values and then carried forward multiple times with different values?
It's carried forward symbolically.
I have one thing to ask. So the rules are in conjunctive, right? So these are like, I want A to hold, I want B to hold.
Yes.
So given an event stream, I can check them independently and say, they both hold, or, if I independently check them, I can still determine if the stream satisfies or does not satisfy the thing. But when I look at earliest violation, is the interaction happens, right? I mean, can't I independently check them separately if I don't care about, given an event stream, I can check the rules independently and I don't have to consider them together to figure out if the event stream satisfies it or not, right?
Only if you're interested in only one rule at a time.
No, I want to satisfy all of them, but I'm going to check them one by one. There's no problem with that.
So if you want to satisfy the set of rules,
Yeah.
I want to satisfy R1 and R2,
Yeah.
then you cannot do that only looking individually. So
That's the part of it.
again, for this example, for this event stream where there's just a request, rule A will never be violated because I can always see some payment sometime far in the future. I can
Yeah,
never
but,
say.
but I see. I mean, so I understand that argument, but I think the argument, if I'm saying, if I have the full event stream, I have it already. It's not like it will happen. I have a characterization, even if it's infinite, I have a characterization of infinite stream. And if I have that, I should be able to check each rule independently and decide that they all either satisfy or one violates, right? That is doable, right? That's what yeah. Because this, I think you are saying that if the stream is not known the future, then there is interaction. I understand that's because for early violation detection. But if I know the stream fully, then I should be able to check them independently.
If you know the whole stream in advance, then the semantics of the rules are defined separately. So you can say, does it satisfy R1? Yes or no?
Yeah, okay.
Does
So
it
that's what I was
satisfy
talking
R2?
about. This is like either you don't know the future. If you don't know the future, then yeah, and that relates to earliest detection.
Yeah.
Just wanted to make sure.
So perhaps the confusion is Isaac's problem is to check the earliest
Yeah,
possible.
no, I understand that. That they will interact.
Yeah.
But yeah, there must be since it's the way I'm thinking is rules are conjunctive. There must be a way of like if you have the full information about the event stream, you should be able to independently check them one by one, and that's doable. But the problem you are studying is not that. You know. Yeah.
So we have a chase process that generates what I call expected events. So these are events that must occur to avoid a violation, but we might have tagged them with some assumptions that we've made. To integrate the expected events with the previous algorithms that don't rely on expected events, I'm going to present a refresher of my individual rule algorithm. Oh, I'm sorry. This chase process of generating new events, we have to guarantee that it terminates, because if I instantiate a body, this satisfies the head, I get a new event. If that can cycle back into the body, then I get this non-termination problem. But if I restrict myself to only looking at acyclic rules, we can guarantee the chase termination. And acyclicity is defined as follows. If I have, again, the same rules A and B, when I have a variable that indicates some data is passing from the body to the head. So for example, if there's a request for some user U, there needs to be a payment by the same user. We can say, okay, this U is going to say this request event can trigger another payment event. And whenever we have an existential variable, we'll denote it as, we'll mark it somehow and say this is also a special case of some data in the head generating some new data in the body. And if we complete all of these edges between the events and what data attributes can generate more data attributes, we say, is there a cycle among these event types that can generate existential data infinitely? And if there is such a cycle, we say that set of rules is not acyclic, but if it's acyclic, then this chase process will eventually terminate. So it's not just the fact that data variables can be mapped from the head to the body, from the body to the head. It's also that they're existential variables, meaning they would generate new data. Because if I just have a request for Alice generates a payment for Alice generates a request for Alice, that might not be acyclic, but if there's an existential variable involved, then we can have these new data being introduced by the chase process, get non-termination. So when we consider the chase process for acyclic rules, this always terminates, which is a result from 2006. So to look at how these expected events in the chase process are contributing to the algorithm for matching rules, I'm going to walk us briefly through the data structures and algorithms for the individual rule case. So if I have the same rule B, request and payment leads to some approval, I'm going to create 3 data structures that are going to hold assignments to these variables. One for holding body assignments, one for holding head assignments, and one for holding extensions, where extensions are just matching between a body assignment and a head assignment. And we'll also give IDs to the assignments to distinguish them and keep track of any gaps that are unresolved by the current assignment. So if I have approval at time 9, I'll generate a head assignment, beta 2, where I'm mapping the variable v to Bob, z to 9, and an unresolved gap where I have 9, the timestamp for z, is less than x. For the request event at time 10, we're going to generate alpha 1 with user Alice time x. We haven't yet a value for y, but we have an unresolved gap. We know that y is greater than or equal to 10 in order to match this assignment to x. And then if I have a payment at time 16 from Alice, we'll generate another body assignment, and then we can join those because they agree on their gaps and they don't have any conflicting definitions, so they're both for user Alice, and one of them defines x, one of them defines y. And then to match an assignment from the body to the head, we note first, say, for the assignment alpha 3, if I don't see any other events, we're going to have no matching head assignment, and this gap that z needs to be less than or equal to 10. So the deadline is 10 for alpha 3. But then I can match alpha 3 and beta 2. It resolves all their gaps, and there's no deadline. So this is a data structure for matching assignments to the body and assignments to the head, and also keeping track of when that match must be satisfied by. So I presented this in my proposal as allowing detection for individual rules. And in order to integrate the expected events into violation detection.
Sorry, can I, in the previous slide, so when you do this algorithm, right, the inference of the deadlines are doable because of the constraints you have, right? I mean, there's some arithmetic going on there to get the deadline, right?
Yes, so in this case, to match beta 2, I need to see an x. But there's no upper bound on x, so there's no deadline for matching beta 2.
So there is something on those constraints, that some reasoning that needs to be done for you to get this algorithm working, right?
Yes.
So okay. And then if those constraints were whatever, so is it discrete time? We're doing discrete time.
Yes.
So if that was like an arbitrary, quantified formula, then you cannot do it, right? So I mean, if I had first order arithmetic there, writing whatever, arbitrary rules, then it wouldn't be done. So what I was wondering is like, so the constraint language you have, this works, but if it's more expressive, it may not work. I mean, so did you kind of extend that? Did you kind of explore? Because it could have been simpler. You could have just said, I'm not going to have addition. It's just going to be bound constraints. But you put the addition. I assume there is multiplication by constant. You can't say 2x, it's just the same thing anyway. So, but is there a kind of, did you explore like if you make it more expressive?
I didn't look at multiplication by a constant.
Oh, you didn't? But I mean, so you don't, oh, okay. So that, I feel like,
I only
do you think that would work? Anyway, so there is, but yeah, I see. So
yeah,
that's what I was trying to
I
get.
only look at these inequalities with constant offset.
Constants, okay. So all right. So that would be the first thing I would like, but I don't know, maybe yeah. Okay. So, but then that bound propagation thing would change, of course, but it might work or not. But for this it works, and then you have some stuff later on. It doesn't work for these constraints, right? So there's some extensions undecidable.
Yes, and the undecidability result isn't making the time constraints more complex.
Yeah,
it's allowing unacyclic sets of rules, or it's allowing cyclic sets of rules. Yeah. But the calculation of the deadline is some satisfiability algorithm. For the individual rules, it's just a conjunction of linear inequalities.
Right.
So it's not even allowing disjunction and all that stuff.
Yeah, but I mean, so what I'm saying is, it's just satisfiability you needed. You can make that much more expressive, and there are such solvers for. But so I guess there must be some things when you get, and so there are certain integer. If you had a lot quantification, then it's satisfiability will not be decidable, so you cannot do it. But so there's probably, it's possible that you can make those more expressive and it may still work, right? So that's not, I mean, that's a possible, we don't know.
Yeah, see, I'd have to think more.
Yeah.
Also, I would say that for time constraints, they're usually not much more than there's a bound or there's a gap that has to happen or some equality. I mean, I haven't seen many examples of timing constraints that involve, arbitrary multiplication or
Yeah, this
exponentiation.
becomes theoretical at this point. It's like, yeah, realistically, there may not be a use case it's worth it to look at. But,
So to pull the expected events from the chase algorithm into these data structures, we add an additional column that says, has this body assignment been chased? Because we don't want to chase it over and over again. We want to say if I have some complete body assignment, I need to create an expected event from it. I need to remember when that's been done. So for example, if I have request and payment, which generates these assignments, one for the request, one for payment, and one for the join of those assignments, we're going to chase that assignment to get some approval event at time z prime, which then gives me a body assignment. But it also gives me a match between alpha 3 and beta 2 that's dependent on y prime being greater than or equal to 15. So now we have a more complicated structure of formulas. Before it was just a conjunction of inequalities. Now we have a slightly more, I'll talk about how this is resolved, but a slightly different storage of these gaps because they might include variables that aren't in that particular assignment. So this is a constraint on the body assignment, and this is a constraint on the head assignment. So given this event stream with just a request, the expected events, payment, and approval, and the possible assignments from those events, we would say there's no violation at time t if when A3 exists at time t, A3 can match with beta 2. Because A3 is, this condition of matching with beta 2 requires that the y prime that's used in A3, or alpha 3, to be greater than or equal to 15. So this becomes a satisfiability problem. There's no violation at time t if when 15 is greater than or equal to y prime, z prime is less than or equal to 10. And additionally, because we're in this online context, we require that whatever the current time I'm interested in is, that time is less than all of the unresolved variables. So these expected events that have to occur, I say these expected events have to be later than the current time. I'm only going to consider satisfying assignments to these variables that are later than the current time. And this problem, this satisfiability formula on the left, is only satisfiable while t is less than or equal to, it's less than 15, which recovers the example deadline where if we just have a request, as long as time 15 hasn't arrived, we can still have a payment that doesn't trigger rule B. But once we get to time 15, this becomes unsatisfiable. Once t is equal to 15 or greater, this becomes unsatisfiable, and we can report a violation.
So is this how you detect the earliest deadline?
Yes.
Okay. So and that's an existential variable elimination.
Yes.
So
And so given the possible matchings we construct, really would be a much larger formula for a more complicated example. We'll ultimately just ask, is this satisfiable if all of the unresolved variables are greater than the current time?
But then that's not, you ask the satisfiability question, but then you also want the that form t less than 15.
Oh, actually, yeah. I just report, is it a violation or not? But you can recover
You
the
can
time.
the existential variable eliminations.
Yeah.
You can do it.
But because we are in the online context, I just ask I do the satisfiability check each time by updating t equals 15, t equals 16, t equals 17. So maybe you could compute this deadline, assume no other events arrive. So yeah, I hadn't thought of that, but previously just in a binary, satisfiable and unsatisfiable corresponds to violation or no violation. Yes, you can't compute the deadline from it. So that concludes looking at these acyclic sets of rules where we use the chase process to generate expected events So that was an extension of the work that we published in Time 2022. We extended it on the suggestion of a reviewer who said, hey, you should consider sets of rules, not just individual rules. And we're still in the process of revising that submission. Next, we'll consider aggregation functions on time windows. So if I have a same event that might occur every timestamp or very often, I might want to ask, I want to look at not the individual events, but some aggregate property of the events. So to gather that set of events, we'll look at time windows on event streams. And we've defined a classification of time windows that include moving windows, like sliding windows, which would say for a fixed length, include every set of events that occur inclusive between those two timestamps, and this slides along the event stream. So I'd like to know some aggregate for each sliding window, or for a tumbling window of a fixed length. So for every, in this case, 3 timestamps, collect those events and apply an aggregation function, collect the events, apply an aggregation function. And we also consider triggered windows. So if I have some other events, like an audit is happening, so the audit starts and the audit stops, we insert these triggers into the event stream. We can have a start triggered window that says, from this time that we have a start event, collect some finite length, some fixed length of events. Or start and end trigger, collect all the events from the start event to the end event. So we define these different time windows of collecting a set of events. And then we apply different aggregation functions in the rules. So we use sum, min, max, count, count unique. So I'll just illustrate with the sliding window and sum. If I look at the sum of the payments from, for a fixed length from time equals 1 to time equals 3, I'll have 140 as the sum of the payments over the events in that time window. Or if I look at the max function over the same window, we say for the sliding max from time 1 to time 3, this is 80. And then these become events in the event stream that I can use in my rules. So we can say the sliding sum from time 1 to 3 is some value compared to another value.
But you are not mentioning pay there. I would have expected you to say for the pay events.
Yes, I simplified the rule, so I really would have pay A, pay some here.
Okay, so you would have that.
Yeah. So I could, if there were different types of events, like deposits and withdrawals,
Right.
we could say the sum of the deposits needs to be less than or equal to the sum of the withdrawals. So if we want to reason about these windows when they perhaps aren't complete yet, we can use Pressburg arithmetic to encode the aggregation functions. So for each open window and the aggregation functions, there's an equivalent Pressburg arithmetic constraint. So if I've only seen pay at time 1 and time 2 with 80 and 60, I can imagine there's some pay event with a time A at time 3, which I don't know yet. If it's time 2, we haven't seen the next pay event. For the sliding sum, I can say there's going to be an event at time 3, which puts into a value S prime 80 plus 60 plus whatever that A is. So we can introduce, just like the chase process, introduce expected events. We can use this pay event as expected. We give a specific value A to it, and then say, well, then this Pressburg arithmetic formula, S prime is equal to 80 plus 60 plus A is going to be tied to the sliding sum event. Or for the max function, we'd say if I have these 3 events, the maximum value M prime is going to be equal to one of them. It's either 80 or 60 or A, and the maximum value has to be greater than all of these events. Well, we can use this encoding of the aggregation functions in Pressburg arithmetic to detect violations. So if we say the sum, the sliding sum has to be greater, less than or equal to 200, and the sliding maximum has to be greater than or equal to 100. Again, the same payment events. At time 2, I expect an event to happen at time 3. I know I'm going to have a sliding sum event with some s prime, a sliding max event with some m prime, which are constrained by those values, where a is a free variable here. And we show that the earliest violation for an acyclic set of rules with aggregation can be computed with similar techniques for the acyclic set without aggregation. So if I look at the head assignments, I have some s prime, where s prime is bounded above by 200. And for the head assignments for, that should be sliding max. For the sliding max, there's going to be an m prime, where we have that Pressburger constraint, and then we also have m is greater than or equal to 100. This formula implies that a is less than or equal to 60. This implies that a is greater than or equal to 100. So my unseen value maximum has to be greater than 100. Sum has to be less than 200, which is upper bound on a. And so I can use the same satisfiability test to say at time 2, there's no violation if here we have true because the events here always appear, these sliding events. We need some alpha 1 with s prime, and we need some beta 1 with m prime, but this is going to be unsatisfiable because of the constraints on a. So to these sliding windows, we rewrite them with Pressburger arithmetic, and then we can do the same type of reasoning which allows us to detect violations as early as possible. So that's the result for acyclic sets. I have a definition in my thesis for if I include aggregation functions, how we define acyclicity, but it's more or less the same if I have some existential variables that can propagate and generate more existential variables. This is not allowed. Dan?
So you're saying that you can do this with similar techniques as for the previous one. Is there some hope of saying that if I give you a set of rules, with these aggregation functions, that you can basically just compute a set of, compute an event stream and a set of rules without aggregation functions that is then equivalent, and just run the previous algorithm on that? Is that doable? Is that what you do? Is it?
Yes. I can't answer immediately yes or no, but it sounds doable. The reason we include aggregation is because this is kind of syntactic sugar for the aggregation functions. So instead of having to write rules without aggregation, we can say, look, we can just write sliding windows or triggered windows, include these in the rule language. But yes, there's some underlying encoding in the original. So yeah, rules with Pressburger arithmetic or something like that.
Okay.
But I'm not sure about that. But it sounds reasonable.
In a cyclic rule, you said you check it syntactically, right?
Mm-hmm.
And do you think there could be a relaxation of that rule, where syntactically it may not work, the syntactic check, but actually semantically somehow they are not cyclic?
Yeah. With the chase process, there's been a lot of work on chase termination beyond acyclicity. So we know that it terminates when it's acyclic, but are there maybe data-dependent conditions? So for certain event streams, maybe the rule is still acyclic, but you're never going to have this non-termination process. So I'm not exactly sure of how relaxed those conditions can be.
Yeah, I mean, I guess that would be any kind of it would be, I guess, a hard thing to show, maybe that, if it violates the syntactic condition, there's always a scenario where actually the non-termination happens or something, but that may not be the case. So it's kind of, what you guarantee is if the acyclic rule that you syntactically have satisfied, then it terminates and then you get.
Yeah, it's a sufficient condition.
But even with rules that have cycles, the real coming with a given a event stream, the chase may still terminate.
I see.
Right?
Could you repeat it?
For a specific stream of events, the chase may still terminate, even the rule is cyclic.
Mm-hmm. Yes.
Right.
Yeah, and that I've seen as could be called a data-dependent chase, or data-dependent termination. So depending not only on the rules, but also on the data that you have. Maybe there's some, you can look at, does it terminate even in certain cases? So finally, we'll look at the reduction, which says that this early violation detection problem in general is impossible if I don't make any restrictions on the sets of rules that are allowed. So a result is that early violation detection is impossible for an arbitrary set of rules. And we show this by introducing the notion of finite satisfiability, which is very closely related, which just says, for a set of rules, is there a finite event stream that satisfies that set of rules? Any event stream, which reduces to early violation detection, because if nothing has happened yet, and my set of rules is unsatisfiable, I can immediately report a violation. If my set of rules is satisfiable, then that is a potential extension of the current event stream. So we can reduce finite satisfiability to early violation detection. Thus, if we can show finite satisfiability is undecidable, early violation detection is impossible. And we do this by a reduction from the empty tape Turing machine halting problem, which says for a Turing machine that starts on the empty tape, does it ever halt? To encode a given machine as a set of rules that will then be tested for finite satisfiability, we use config events or configuration events, which are meant to simulate configurations of the Turing machine. So for this particular initial configuration with some state at 0, it's looking at the leftmost cell on the tape. I can represent this configuration as 3 events, given some time, some index to sort them, but the center cell, the center attribute will hold the tape contents, the leftmost attribute will hold the state of the machine, and which tape contents the state is over indicates the read head position.
Can you say that last sentence again?
So with the configuration of the Turing machine, we have to code the tape, the state, and the position of the read head. So the position of the read head is just wherever, whichever tape cell the state is given. So I'm not, even though I could write the state here, that the state is, the read head position is not over this cell.
No, so the head position is the 0, 1, 2, is that correct?
The, this set of events is meant to mimic this configuration, an initial configuration.
No, so let's see. So you're saying,
And
is this thing a blank? Is it a character?
this is the blank cell, the blank symbol, and these are some delimiters that say the left and right ends of the tape that I've explored so far.
Okay. And but 0, 1, and 2 denote positions of the tape.
Yes.
And they're not time, they're data.
Yes.
Is that correct? So these are not timestamps. 0, 1, and 2 are not timestamps. There are part of the so in particular, your hardness assumes that you need to have infinite domain for your data.
Yes. And the reduction that we do, it uses slightly different syntactic language than the original rules, but we show that the 2 languages are equivalent because it's easier to express without the timestamps.
It's easier if you tell us there are 3 reductions going on here. Turing machine to data log to 1 integer attribute data log, and then from that you to your rules. That would be easier to understand.
Okay. So we do the reduction from finite satisfiability, not for our rules, but for a data log, which is a similar syntax, but it doesn't allow certain features. So we do the reduction. We show that data log is not finite. The finite satisfiability problem for data log is undecidable. And then we show that there's an equivalence between data log and our language.
And is the data log result was known? Is that existing result or no?
No.
Also, data log finance.
It's a data log syntax that borrowed for the event stream context.
But no. But what I'm saying is this wasn't shown for data log finite satisfiability is undecidable. For data log was not shown either.
We do it with a particular variant. I
For
don't
that
know.
variant, you don't.
Yeah, for that variant, we don't know.
Because to me, I mean, I was going to ask, like, I mean, going from going from data log to your rules Is that the challenging part of the encoding, or going from is it? I mean, I feel like your rules are. You can see maybe going from data log to your rules.
Yeah, so data log in databases it doesn't have existential variables in the head. It's not as expressive.
I see.
So our rules include existential variables in the head, include these gap atoms.
So therefore, what I'm saying is encoding data log with your rules to me seems like doable. I mean, it's like I think the significant step is going from the Turing machine encoding to data log, right?
Yes.
That's the game.
Yeah. Yeah, so that the step between this data log language and our rules is not very difficult.
Yeah.
What's more difficult is showing that each Turing machine has
Yeah.
data log rules. So I'll represent this set of events as a table which just holds the configurations of a Turing machine computation. So we can say this segment of the table represents the first configuration in the empty tape computation. And if I have a computation, a sequence of configurations, then we can represent this in that same set of events. So we can say if there's, my next configuration is move to the right, change state, and write a C to the tape, then I'm going to store a set of events later using the index in the same set of config events. We'll encode the initial empty tape configuration using a rule. So if M starts in S0, we'll have a vacuously satisfied rule that says the configuration table should include that initial configuration. So we have to start the config events in the same way that we start with the initial empty tape configuration. We'll use the next events to propagate a single configuration to the next configuration. So we'll say if the tape contents and the state for index 0 should appear next at index 2, and the tape contents for index 1 should appear in the subsequent computation at index 3. So for example, if I have a transition at 0 on the blank symbol, where I write a C, move to the right, change state to S2, then I want to encode a rule that enforces that transition on the events that I see. So I have if the next table holds certain contents, the configuration table holds certain contents, then we're going to write the next configuration, or one line at a time, the next configuration, the subsequent Turing machine configuration. We also want to make sure that if the rules are finitely satisfiable, then this corresponds to a valid configuration. So we can detect non-valid computations with one more event, which introduces some error. So if I detect an error, it's going to make that computation non-finitely satisfiable, or non-finite. So if I have that following configuration, if I somehow say, well, I'm going to propose a set of events, it has at index 3, the tape holds a C, but also at the same index we have a blank symbol for S2. This is not a valid configuration, so we need to make sure that this corresponds to a set of rules that's not finitely satisfiable. So I'll introduce this error event. If there's a malformed configuration, so if there's some index in config that has different tape contents for the same index, I'm going to generate an error event at some time 0, and then propagate errors infinitely. So if there's an error at time 0, error at time 1, at time 2, and 3, and so on. So this is to get the if and only if part of the reduction, so that the set of rules we generate is finitely satisfiable if and only if M halts on empty tape.
Your rule doesn't have inequality. So A not equal to B, you mean for each pair of distinct symbols, you're going to have a rule.
Yes. Yeah. Because the tape symbols and the tape symbols set of states are all finite, so we can do the inequality comparison because it's a finite set.
I'm a little bit confused here. Is the X time variable?
No.
It's not.
It's an integer variable.
So you are not using time constraints in the this encoding.
That's right.
Let's see now if you have prescriptive arithmetic and so you have arithmetic on the things. So index becomes like an ordering them. I mean, you are using it to order the things, although
Yes.
you don't. But then, okay, here's my confusion, right? So if the time is not mentioned, this can appear in any order, right? Which I guess doesn't matter with this encoding. I mean, although you are saying error x implies error x plus 1, in the stream that we see, error x plus 1 may come before error x. As long as there is an encoding, the ordering of the event stream is now completely irrelevant. As long as you see the events that you should have seen, that's consistent with the Turing machine execution, right? That's basically what you're saying. And if you don't, then you start the error process. But you see what I'm saying? So it seems like the order they appear is not related to execution of the Turing machine.
So
just the index is the one.
Yeah, the order of the index does not need to be associated with the time domain.
Yeah. So okay, this one.
So that's what I'm saying. You need to tell us 3 reductions
No, that's fine. I
separately.
No, you are
Because
saying
this one has no timestamp.
Yes.
Next one has no timestamp, but now
Yeah.
index and next are separate to 2 different relations. And the last one with timestamp, that's your language. So right now we're all
I
confused.
see. This is the different encoding.
Yeah.
With time, without timestamp.
Yeah.
Okay.
Yep.
So that concludes the fourth and last section of presentation about the impossibility of early violation detection. So the outline of my presentation corresponds with how my thesis is organized. In chapter 3, I talk about rules without data. Chapter 4 covers sets of rules with data. Chapter 5 introduces aggregation functions, and then chapter 6 presents the reduction. So a summary of my contribution to this problem. So we improved the size complexity of the translations for 2 subclasses of dataless rules to LTL. We provide algorithms for detecting violations of acyclic sets of rules at the earliest possible time, including rules with aggregation functions. And we show that this problem is impossible for arbitrary set of rules. Some future directions that I think would be interesting to take this work would be to look at violations of more complex time constraints, as Tevin, you mentioned earlier. Can I use a more complex language to compare the timestamps? Or to look at richer sets of rules and whether or not they have any algorithms or efficient algorithms. Specifically of interest is negation, because my language doesn't have a way to say an event does not occur. It doesn't have negation in the body of the head. And then disjunction, maybe to say in some workflow we choose between 2 sets of events, and either one will satisfy the rule, but we don't have to see them both present. So thank you for attending my defense, and I welcome questions now.
Thank you. All right, questions?
Yeah, maybe let's do audience first.
Okay, let's see. Audience, do you have any questions? Just unmute and speak. Well, I guess not. All right.
Continue discussion.
Yeah, well, the questions here.
So let's start the.
Is it still open part? We have
I don't
audience.
I'm ready to go to
To the closed part?
Yeah, no, let's not torture the audience.
All right. Okay, so audience, you're excused. Let's we move to the closed part of the defense.
Should I just put them all in a waiting room?
You can now. Okay. Well. Oh, we don't need it. We don't need it.
Yeah, you just close the.
We just close the Zoom. That's right, exactly. We don't use Zoom. Good. So you didn't mention optimization. I think the what Tevik raised there was the if you say t less 15 t happens, then you don't have to running an algorithm every step. You only check are there relevant events happening. If it didn't happen, no change. Do you have any idea of how much savings you can get?
Probably a lot. Well, savings in terms of.
In terms of each step, at each time step, you run the algorithm, and that right now you have this complexity, let's say x, right? So if you incorporate that particular kind of savings, it's going to come down. How? Well, I don't know, percentage of time maybe savings.
Mhm.
Because you run experiments, you have some kind of estimate.
That's true. When I did implement most of the algorithms I presented, and then experimented on some simulated workflows, and by far the most time that was taken was by the satisfiability check at each time step. So I'm sure it would it would make these more feasible, or it might make it more feasible to save the deadline and then only recheck once that deadline is reached, assuming no other events have happened, assuming there's no update.
Yeah, that was going to be my question actually. Did you implement this stuff? But so yeah, I mean, so you implemented, I mean, all of them or most of them, like, and then ran experiments?
Yeah, most of what I implemented was the acyclic sets of rules.
Okay.
So it was for the acyclic sets and implementing the chase process. Yeah, I implemented that, and then I used a previous student had a simulator to generate event streams, and then I would apply that and determine mostly whether or not it was feasible. So whether or not this detection process could run the algorithms, including the satisfiability test, within the arrival time of the next set of events.
And then for the satisfiability check, what did you use?
I used Z3.
Z3, yeah.
Yeah, and I think I only spent, I don't know how long, a year or so, 2 years with Z3, and I think more time with Z3 would be a lot better just to understand, because it's a really powerful tool. And
Yeah.
I would just use it as, is this satisfiable? And I think there's a lot of incremental optimizations you can do, which also, in my case, if I have a massive formula and one event arrives, that formula might change just a little bit.
Right, yeah, so then they have incremental, how do you call it, they have optimizations on that too, but gets to implementation, yeah. But I don't think they fully support existential variable elimination, but since you are doing arithmetic constraints for that domain, yeah, you can get the complete existential variable elimination. I don't know if C3 does that, but I think, yeah, I don't know. They do some combination. They can't do it for all theories they support, because some of them you can't do existential elimination, I think, variable elimination. But for sure.
So, in your reduction, yeah, there was some stuff because I guess you were reducing not quite to your rules. You were reducing to some intermediate language, and then there's a reduction from that intermediate problem to your rules. In the end, when you end up reducing to your rules, right, can you say something about what type of data you need in the rules? Like do you get away with the sets of data being finite, as in depending on the, let's say, on the state space and the alphabet size of the original Turing machine, or do you need the data to actually be an infinite alphabet as well?
So an infinite alphabet.
Like the integers. Like you need the data to contain integers.
Yes, in order to encode the indices, the indices, you need infinite domain for that.
So you do need an infinite domain on the data itself.
Yes.
But that means you also need to have some constraint language on the data. Like you need to have some constraints on the data to ensure. So what types of constraints on the data do you need in order to ensure understandability?
Equality and inequality.
Equality and inequality. That's the only thing you need.
Yeah, I think that's why I thought with 3 the plan, the map for the reduction would help. Because eventually it will reduce to your language, which has the ordinary data with equality, inequality, and timestamp.
Mhm.
Because these integer attributes become timestamps in the end. So,
Oh, okay,
yes.
so the data is, the data itself is just finite.
Yeah, that's right.
The
It's
da-
only equality, uninterpreted data, with equality only.
You are not saying finite, it's uninterpreted.
Uninterpreted, with equality only.
Okay, so
And
but
it's
it's
infinite.
infinite, but only with equality and inequalities. Okay, so what happens if you restrict your data to finite?
I think as long as you can represent Turing alphabet, states, and that'll be adequate.
But the chain of being able to chain to form this sequence of configurations.
But that becomes the
So can you-
the timestamps. Right?
But suppose if your data, if all of your data is finite, couldn't you represent every data combination as an event name? Like if the space of possible data is finite.
See the three reductions. You really need that in order to. First reduction, you need infinite. You need integers. Second reduction, you still need integers. But now the language, the data log language, each literal has only one integer variables. Still
Okay.
integers. Third reduction to your language which has no integer attributes. Only timestamp plus the uninterpreted data. With equality.
I only
doesn't-
claim
I don't
infinite.
understand when you say uninterpreted.
I only that just means that there's no evaluation of some predicates like inequality or addition.
There's no two. You can have an infinite domain.
It's just constants. Constants that can either
Yeah.
be equal to each other, or not equal to each other.
That's right.
All we have is equality, non-equality predicate, an infinite domain. So don't think integers. Integers have order, right?
That's right.
So, but
Yeah,
think of an
but
infinite domain.
you can say integers, but you're not, but integers with only equality and equality.
Yeah, but then it's like, then there's no arithmetic. It's,
Yeah, yeah,
exactly.
yeah, yeah,
It's a domain, infinite domain with
Yeah, yeah.
equality. So that's what uninterpreted says.
Yeah, but still, I mean, like but infiniteness appears important.
Yeah, I claim infiniteness. I'm not
Okay.
sure. I'm not sure
Because-
about the finite data domain.
The two columns in config, the tape contents, you don't need infinite. You only need to cover whatever tape contents an alphabet is plus little delimiters. And the state, again, you don't need infinite set. It's just as long as it's enough to represent the states and plus the markers.
Okay, but then can you tell me what goes wrong in reducing so suppose I have finite data set, and then I want to reduce that to data plus rows, because then I can have if my domain for where the data comes from is finite, then every event comes with some finite set of data. I can just encode it in the event name. Yes, I can just say.
No, there is an infinite thing going on. It's a timestamp.
Yeah, but I can say that I encode that in the event net with the timestamp. That's really the only. I mean, I'm just saying that if the domain for the data is finite, why can't I encode every event in just the event name and timestamp, of course? Like what goes wrong with that?
As long as your language has a way to recognize what the encoding is, the encoding may not be expressed in the language. You still need to say, oh, the state is this, and that particular symbol, the particular symbol on that cell is this.
Yeah, but that is part of the like since you have rules that say if event cat then event dog, right? Then I can say if event cat 125 then event dog 452, right? But where 452 depends on the 125 because 125 just comes from a finite set. Am I
Good
missing?
question.
Well, I mean,
Question.
I think but I'm looking at the dissertation. So I think the dissertation is basically data log plus with one integer variable reduction. And then going from that to your language is doable. Yes, so I believe that, although that's not, I don't see that you discussing that. but I think you probably maybe not in that chapter, you stop at data log plus, but I think that's the part you're asking.
Well, it seems like Daniel is asking about the finiteness of the data domain.
Yeah.
If you say if all other data is finite, the only thing that's infinite is the integers, is the reduction still possible? I'm not making that claim. I don't make it in my thesis.
But I don't think
Good
it is to, yeah, I don't think that's what thesis
Okay.
claims.
Okay.
So I think what he's saying is data log plus. I think Jean-Marie is saying a stronger result, but I looked at the thesis, so he, so if we are agreed data log plus with one integer variable is translatable to your rules using infinite domain, which I think that should be definitely doable. That's what the claim is in the dissertation.
Okay.
And then can you make it more restrictive? Is I think another claim.
Okay.
You have another paper, right? Which is
that won't make a big
yeah. But I think I was going to ask a little bit also more practical thing. So, I mean, I know how you started, with the dissertation, major exam, and then it was like workflows, like this, business process management stuff. But eventually, it's nice categorization. I liked it. You developed this language. It's stream processing in a way, right? It seems like applicable to networks. Like network streams, and now with the software-defined networks, this is like an area. It has been around for a while, but people have started looking into really verifiable, network control. So I don't know if you looked at that. So think of this as a monitoring mechanism for networks, right? So you can imagine applications to security domain or maybe some protocol violations. But this to me, like network packets are coming in, you're monitoring it, and you're trying to find the early violation of things. So if you look at anything there, I feel like that could be an application domain.
No, I haven't looked at network packet streams. Most of the event streams I looked at were just some uninterpreted data, or mostly focused on timestamps, or in the context of business process management. So these are activities that are happening on the order of days and weeks, rather than maybe the millisecond timescales that would involve.
No, I like the way you kind of formalized and generalized it, because now it's like, now it's like clear. This framework could be applied to other domains too. It doesn't, to me, like now, too restricted to business processes, right? So it could be just an event stream with timestamps, and
And we don't assume an underlying workflow. So we don't assume anything about whatever is generating the event.
you just have rules.
Yes. Some work does. They say, assuming that this is the workflow, and I have the rules, maybe we can do some more earlier detection, because I know that, or like I have some assumptions about the event stream. I just looked at rules.
Yeah, I think in the verification domain, this evolved to runtime monitoring and verification. So what you are doing is basically, there's a conference on, if you continue, I hope you continue the research. So runtime verification conference.
I presented I had submitted a poster, but then they let me present in one of the sessions.
Yeah, so that's the, I would say, most directly applicable, this kind of, they look into this problem in general, but it's also pretty applied.
So in your introduction, there was somehow less of the literature survey than I sort of anticipated. Is it just because the surrounding literature is too vast to actually survey, or is it because there's too little to say meaningful things about?
I included most of the related work in the end of each chapter.
Okay.
So each chapter at the end is a related work section.
But so can you just talk a little bit about, in the bigger picture of things, right? Because as far as I understand, this early verification problem, you're introducing it, right? Like it's not something. So has it been introduced for similar rule language? Like has that question been introduced for similar rule languages? Like how, or were you the ones to introduce time to these things? LTL has been around forever.
LTL has been around forever, and also this idea of verification for a set. Do I have some conflicts between my rules? Can I detect earlier? I don't think that I wouldn't claim that I'm the first result of early violation detection, maybe the first person to use that term.
Okay.
But yes, other people look at variance. Often they don't look at quantitative time constraints. They look at, I have some ordering, like a request and then an approval, but they don't look at, is the gap restricted by this inequality where I have constant addition or constant subtraction.
Okay, so particularly that, like, so the key difference is between you and previous work is introducing just addition and motivating that from practical applications. Is this?
Yes.
But also,
That's the reason.
there is one thing I'll say. So LTL, if you look at the regular LTL without time constraints, right? Vanilla LTL. The lightness properties are the best characterized as the ones that have an infinite counterexample, infinite path. So one could say that a significant portion of LTL properties cannot have early detection if you don't add time constraints, which is you see what I'm saying? Like inherently LTL, if you say something is eventually true, there is no early violation detection. It's infinite stream. So it's only violated when you have the full infinite stream. So therefore, this question doesn't make sense for vanilla LTL. Once you add the time constraints with your rules, now you have to create this problem of early violation. I think in LTL plus time, timed LTL variations, this may have, I don't know if people have looked at that, but I think that, monitoring, runtime monitoring stuff I've seen there. But yeah, so I think I would say that that's why it's kind of like more specialized, right?
Yeah, one thing that a lot of the related work or previous work use is they assume maybe I do have some data, but the property is either in LTL or it's already encoded as an automata. So it says, and again, these don't have quantitative time constraints, which I think is a great area of application because business rules or other similar rules say there's a bound on when this thing happens. I need it to happen, not eventually, but I need it to happen within some constraints. So including data and quantitative time constraints is the contribution.
Yeah, so I mean, maybe trying to make that as clear as possible, and like early on in the thesis. I mean, there was only a week between getting the thesis and today, and so I haven't had time to look at it very carefully. And it could very well be that you're saying it somewhere, and I just didn't take it up. But trying to make that come out, as early as possible is probably would be great.
Yeah, so probably introduction should also have related work that's about a problem, not the techniques. And that would make it a little clearer.
Yeah.
Yeah, I mean, one revision suggestion would be like, if you are going to add related work, LTL is very generic, right? So you can immediately go to, look, we are doing time one, and then just focus on actually timed LTL stuff and that area rather than LTL in general, which is huge. So you just acknowledge that, there's this LTL, but what I'm doing is more specific. I have discrete time and discrete time LTL. So that is actually the relevant area for your work, not real-time LTL, which is also, people have done that, but then it's like real clocks, which is a whole different thing, right? So where you have discrete clocks. So the things that are really relevant to your work is discrete time LTL papers. So and some discussion on those, like how yours differs with that, will be the address what you're saying.
Yeah. At least as an outsider, I had a hard time understanding, where your work fits in the bigger context of all of the things that are out there.
Okay.
Yeah. Okay. So minor nitpick. I think at some point you say that if you show that the early detection for early violation detection is undecidable, then it's futile to try to design algorithms and software for it. So software verification does this all the time.
Thanks for making one. We work on undecidable problems all the time.
So you might want to moderate your language.
Okay.
Because undecidability. I would even make it more, even generalize that. I feel like in verification, looking at worst case complexity is really people. Because after, because of Z3 type of stuff, right? So worst case complexity is terrible. And people use it. So I think worst case complexity for verification domain, people stop looking at it. But it's still, in analysis, yeah, I mean, it's an important result to show, of course, undecidability boundary, and NP completeness, whatever. But at the same time, in practice, what is really relevant is, do we have a solver that works, that can find bugs, So yeah, I think that's the kind of more general point of view.
I have a few more, but I'll let you go.
No, I'm good. That was, yeah, I think it's good.
So in your first chapter on dataless rules, is the motivation for doing dataless rules is like sort of because you can? I mean, because everything, or is there some motivation for dataless rules as well?
Well, my motivation would be because LTL has already, it's propositional logic. It has, at each timestamp, is a proposition true or not? And so it's maybe a more pure form of the rule language rather than including some data. It's just at each timestamp, I can look at a finite set of propositions, determine whether or not they're true, and keep going with the monitoring.
So let me add. When we started on the dataless rules, we want to do detection.
Mm-hmm.
How do we start? Well, pick something simple so we can grab, get our hands wet and work on things.
Yeah,
so dataless was the first thing. And at that time, the earliest detection wasn't even known yet. We didn't know what happened. So eventually we did that, the MAE and the Central Journal publication, and then later we were like, okay, so what he's working on is really the earliest ones.
Mm-hmm.
So it's kind of get in the field, and then now it's a piece. So
Okay, yeah, but somehow, but then acknowledging somehow in the beginning that we're doing it because we're trying to solve this complicated problem, and the complicated problem, actually in the end turns out to be hard. But there are fragments that we can do, and there's stuff in between without reason. It's a reasonable narrative, but it should be said. Let's see. Also for your dataless rules, you're creating LTL formulations that are exponential in your subrules, right? And then for model checking LTL, the algorithm are probably exponential in the so you get some double exponential algorithm. Something is this what's going on? I mean, I don't know what are.
he doesn't do model check.
Yeah, he's not. He's just looking at stream, right?
Yeah. So once you have a machine, then it's just matching.
Okay, so you have a single exponential time automata and then you just run it on that exponential time automata. Okay, so you have so for some class of dataless rules you ended up with a single exponential, and for the general class you ended up with double exponential size automata. Is that correct?
I would have to check if the automata construction is exponential or not.
Okay.
From LTL to automata.
It is exponential.
Yeah,
Is it exponential in what?
It's exponential in the size of the formula.
Yeah, so then the LTL formula was exponential in the rules.
You get
right?
another exponential.
The automata is exponential in the formula. Yeah?
Yeah.
So now, obvious question, right? Do you need to have an automata? I mean, do you need to have an automata that is double exponential in the size of the rule?
Is it a lower bound you're asking?
Lower bound, upper bound algorithm. I mean, in particular, you end up with an algorithm whose running time is double exponential.
No, the algorithm's running time isn't double exponential. The size of the resulting formula is double exponential.
Even for the first one,
Oh.
even for the size of the resulting formula is single exponential.
Yes.
The
Okay.
running time of the algorithm becomes double exponential.
To construct the machine.
Yes. And then run it, right? I mean, you run it, it's linear in the size of the machine.
Yes.
Yes?
Yes.
Great.
So
Do you need that, right? Double exponential
yeah,
is bad.
let me give a guess.
Okay.
What he thinks. You have a technique for single linked acyclic rules, graphs and so on. Right now you're changing. You're translating to LTL formula. If you take the graph, translate directly to a machine, I don't think you're going to go double exponential. Am I right? You take this graph from the singly linked acyclic rules and just generate a finite state machine from the graph. And it's going to avoid at least the one exponential explosion.
But that finite state machine doesn't have the universal. It doesn't have the semantics of the rules.
Oh,
If you're
that, I'm not saying the graph. I'm saying from the graph, you generate the state machine.
the generating the state machine from the graph, you're saying it's like
Yeah.
this linear or very, very small.
I don't know. I mean, yes, I think that's definitely will avoid double exponential because from the graph to
I think
LTL?
you are now making claims that are not in the dissertation.
That's
let's not speculate on
Okay, all right.
It's a good thing to investigate, but I think currently it is what you wrote, right? So you're going from rules to the LTL, and then from LTL you can construct the automaton to process the stream. So you are going to get another exponential blow up when you go from LTL to automaton. But I think, well, that exponential, probably there are some reasons for that exponential. I just covered that algorithm, so I mean, I think it is.
It's a negation.
It really
right?
comes down to until operators in it.
Are you asking me why LTL to automata is exponential?
Yeah, I told it, so I know I'm not asking that, but I would say that it's possible your LTL formula will not get that double exponential. It's because it's a particular type of LTL formula you're constructing, and I think.
Oh, you're saying that if there's no until operators, it might not be.
Yeah. I mean, it's I think it really depends on, I think, the until.
There is one until operator
Yeah.
in the formula.
Okay. So I think that, so there may be a result that, like, the worst case may not apply in this case.
Yeah.
So there may be a tighter bound, right? So.
Yeah, no, at least it's something that appears on the surface as an interesting thing to investigate. Okay. So you made an unusual choice of putting your CV at the beginning of your thesis.
That's UCSB.
That is UCSB.
No, this is the first thing. That's our format.
Okay.
Yeah, that's our format.
Okay, all right. And because there's stuff in the CV that is not in the thesis, and there's.
The CD is now that's the format.
Okay, interesting.
It's not his decision. Just
Okay.
follow the template.
Okay.
Yeah.
All right. Next slide.
Okay, so should we excuse Isaac?
Sure.